Okay, continuing along, folks. Let's talk about the various processes of photochemistry and the decay of excited states. Okay, let's see. Here we go. Okay, so the first thing, just setting up a few definitions. Our primary process, products are formed directly from the excited state of a reactant, or the secondary process, where the products are formed from the intermediates that are formed directly from the excited states of a reactant. So for example, if we set this up like a mechanism, we can say A absorbs light and forms some excited state. This process is crazy fast, like something on the order of 10 to the minus 18 seconds for the lifetime. And then a star may directly proceed to products. And overall, if we, typically that would be much slower. So that step is rate determining. And so if we balance that overall, it looks like A goes to products, and we say that happens with rate constant Kp, photolysis rate constant. However, in our secondary process, on the other hand, a star may form some intermediate, and that intermediate goes on to form products, right? So we can quantify that with the quantum yield, and typically we do that with the primary quantum yield, so the things that happen directly from the excited state. So we could think of that as the number of events divided by the number of photons absorbed. So for example, let's suppose that our molecule, or we have 100 molecules absorbing 100 photons, and only 50 of them lead on to photochemistry. That would be a quantum yield of 0.5, right? Or similarly, if we think about this in terms of the kinetics, it's the rate of whatever process we want divided by the rate of photon absorption, right? So we know that and that rate is going to be related to the rate constant. So we know the rate constant of photon absorption is very large, whereas Kp is going to be much slower than that. So that would give us a quantum yield that's less than 1 if that process is much slower than the rate of photon absorption. And so thinking about some examples, a few of the things that can happen with excited states. So for one, there's our absorption. This process is very, very fast. And this is by no means like an exhaustive list of everything that could happen, but it's just an example of some of the things that might happen. So for example, our molecule might fluoresce. So that excited state returns back to the ground state and emits a photon with a frequency that is less in energy than the photon that was absorbed, right? So that would be fluorescence. Our molecule could also go through non-radiative processes called internal conversion or even intersystems crossing. We'll go into those in much more detail in 362. But what's important to note is these processes are typically very slow, okay? So if we have, if fluorescence is observable, then we might not see these things. The fluorescence might happen faster than what these processes could happen. Or if photochemistry is quite fast compared to the internal conversion or the intersystems crossing, then we would see that photochemistry happening more readily than we would see the slow processes happening. So, right, to continue on with that, we could say then S star goes on to products at rate constant Kp. And so if, let's say, we wanted to know the quantum yield for photochemistry, right, we would take the rate constant Kp, and we'd have to divide it by all of those other rate constants. So the rate constant for fluorescence, plus perhaps the rate constant for intersystems crossing, plus the rate constant for, let's say, internal conversion, right? So as you might imagine, if this Kp is quite large, if it's fast, and the rest of these are small, right, they're slow, then we would have a large quantum yield for photochemistry, right? Or we could also think of the quantum yield for fluorescence, for example, right? So I'll write quantum yield F, and so then that would be Kf divided by all, oh, and then sorry, I'm going to also add that to all of the other processes. So I would also add that to Kp, right? We have to think of it as the total. Or in other words, if I want the quantum yield of fluorescence, right, it'd be Kf plus KISC plus KIC plus also Kp, right, if we wanted the quantum yield for fluorescence. So we can also use this kind of dynamic to understand how lasers work. And we'll go into this in much more detail in 362, but I did want to spend a little bit of time talking about this in this class because it's interesting when we think about it in terms of the time. So if we imagine a molecule here in its normal thermal equilibrium, right, where this represents the ground state and this is some excited state. Our normal thermal equilibrium says most of them are in the ground state, maybe 1 out of 1 mole or something like that is in the excited state. However, not many of those molecules are in the excited state. So we have to pump all of those molecules up, typically using another form of radiation. So it could be another wavelength of light or another form of energy. So we pump all those molecules up into some excited state. So not all materials make good lasers. So what makes a good laser is something that will do the following. So we have some extremely short-lived excited state, and we pump them up to that short-lived excited state very quickly. And now presumably there's going to be some slow process to take it to what I'll call a metastable excited state. So in other words, that metastable state can live for just a little bit longer in time than our short-lived excited state. So that slow process is typically going to be non-radiative, like inter-systems crossing or internal conversion. Again, some slow process, right? So what that does is it creates a population inversion, right? So we get some very fast process that takes it up to here, and now some very slow process that brings us to a metastable state. So we'll get a lot of molecules in our upper lying excited state compared to our lower lying ground state. So that's what we have here, this population inversion. And then now finally, they'll go to some state in which emission of light is the most likely process, which is very quick. And because we've put this lag, right, because we've pumped a bunch of molecules up into this excited state, we will get a lot of light being emitted. And to further amplify that light being emitted, this is all typically done in some type of cavity where the length of that cavity is directly proportional to the wavelength of light emitted. So that's should be a lambda right there. And thus we will get this maximum constructive interference occurring that amplifies how much light we can get out. So this is showing a 3-level laser. The same thing could also be achieved with a 4-level laser. What's important to note is this time lag. That's what makes our population inversion, and that's what gets us emitting a lot of photons from a single process. Okay. And also typically lasers are used quite frequently in photochemistry because based on this cavity and the fact that this is occurring in this quantum way, we get one specific wavelength of light being emitted from a laser. So that's particularly useful in photochemistry where we can select one single wavelength of light. Okay, and the next video we'll talk more about the photolysis rate constant, Kp. I'll see you then.